So far we have seen symmetric key cryptography. Today we will discuss public key cryptography. Secret key cryptography uses single key to both encryption and for decryption. It must be presented at the sender and at the receiver. This key must kept secret. Let's see security services provided by symmetric key cryptography. Here, the sender will encrypt the message and send that encrypted message over the unsecured network. Because this is encrypted, nobody within the network cannot read. Means symmetric key cryptography will achieve confidentiality. Regular symmetric key encryption with shared key does not provide the integrity, authentication, and non-repudiation. Nothing prevents attacker generate a random message and send to the receiver. Receiver will then decrypt and accept the message. See here, if Eve generate some random message and send that message to Bob, Bob will have no idea whether this message is coming from the Alice or from somebody else. He has to decrypt with his key and he has to accept that message. So it does not provide authentication and integrity. Symmetric key cryptography can also be used for authentication if you use authenticated encryption mode of operation like GCM. If one of the communicating entities, either Alice or Bob, try to cheat other, it is impossible to decide who is right. Means it does not provide non-repudiation because both of them having the same key. Means anyone can generate the same message. So we cannot decide who is actually cheating. So symmetric key cryptography will not provide non-repudiation. Let's see the motivation for public key cryptography. Symmetric key crypto system have two essential disadvantages. One, key management and distribution. Two communicating entities need secure channel. See here, both of should exchange key securely, so they definitely need this secure channel. Without that, they cannot exchange the key. Two people need secure channel to distribute key. A communication system with n users, all of them are using symmetric key cryptography to communicate with each other. It needs n into n minus 1 by 2 secret key exchanges. Whenever a user wants to change his key or a new user wants to participate in the system, n minus 1 new keys have to be generated and distributed over n minus 1 secure channels. Means we need n minus 1 new keys and n minus 1 secure channel for one new user. Second problem of authentication. How can we know that the digital message is sent by the claimed sender? When there is a conflict between sender and receiver, it is impossible to decide who is right because both have the same key. Any message made by one of them could also have been made by other. One more problem, if we use the distribution center, what if key distribution center is compromised? These disadvantages prompted researchers to look for a different kind of crypto system. Public key crypto system was first described by Stanford University professor Martin Hellman and his graduate student Whitefield Diffie in 1976. Their paper described a two-key crypto system in which two parties could engage in a secure communication over non-secure communication channel without having to share a secret key. Influenced by Markell's work on public key distribution, it disclosed a method of public key agreement. This method of key exchange known as Diffie-Hellman key exchange. In 1977, a practical method of non-secret encryption was invented by Ron Rivest, R.D. Shamir, and Leonard Adelman extended this idea of public key cryptography. In 1973 and in 1974, British cryptographers at UK Government Communication Headquarters (GCHQ) already implemented these two systems. They used for military, so their discovery was not publicly acknowledged. UK government declassified it in 1977. We have seen these two problems, key management and problem of authentication. Public key cryptography can address about two problems. Public key cryptography is a cryptography system that uses pair of keys, public key and private key. Public key can be distributed to the public. Private keys are secret, known only to the owner. Public key crypto systems simplify the key management and also used to generate digital signatures. Digital signature provide integrity, authentication, and non-repudiation. Public key cryptography is based on special mathematical functions that are relatively easy to calculate but very difficult to invert. These special functions are called one-way functions. Some examples of these special mathematical functions are multiplication versus factorization. It is easy to compute the product of two prime numbers, but there is no known method to factor the primes other than by trying all possible combinations to arrive at the primes themselves. Suppose we have two prime numbers 23 and 17, and we want to calculate the product. It should take almost no time to calculate the value, which is 391. Now suppose this 391 is given and asked us to tell which pair of the prime numbers multiplied together to obtain that number. We can come up with the solution, but calculating the product took less time. Factoring will take longer time. The problem becomes much harder if we take very large prime numbers. RSA algorithm uses this method. A major advantage of RSA is its simplicity. Second one, exponentiation versus logarithms. Exponents and logarithms work well together because they undo each other. They are inverse functions. It is relatively easy to calculate. Suppose a equal to 3 and x equal to 6. It is relatively easy to calculate 3, 4, 6, which is 729. But if you start with the number 729 and need to determine the two integers a and x, so that log a of 729 equal to x. It will take longer to find the two values a and x. Diffie-Hellman uses this idea that finding logarithms is relatively harder than performing exponentiation, third one scalar point multiplication. It is easy to compute the scalar point multiplication but very difficult to obtain its inverse. Elliptic curve cryptography uses this method. Key exchange is a main application of public key cryptography. Public key cryptography could theoretically also be used for encryption, but this is rarely done because public key cryptography is too slow when it compared with symmetric key cryptography. Let's see RSA encryption algorithm. Before getting into details of RSA algorithm, let's discuss concepts used in RSA algorithm. One is GCD, greatest common divisor of two numbers is the largest number that divides both of them. For example, if you want to find the GCD of 54, 24, one of the easiest way is to factorize these two numbers. Prime factorization of 24 is 2 into 2 into 2 into 3. And for 54 is 2 into 3 into 3 into 3. Here common values are 2 and 3. So multiply both of them, you will get GCD 6. We can calculate GCD of two numbers easily by using Euclidean algorithm. Divide the larger number by smaller number. If we divide 54 with 24, then we will get remainder 6 here. Then divide the smaller number with this remainder, then we will get remainder 0. Take the smallest non-zero value. Here it is 6. So GCD of 54, 24 is 6. Extended Euclidean algorithm will compute GCD of two numbers and integer coefficients of that two numbers. If the GCD of x, y equal to r, then there exist integers a and b, so that xa plus yb equal to r. By reversing the steps in Euclidean algorithm, it is possible to find the integers a and b. We shall do this with previous example GCD 54, 24. That can be written like this: 54a plus 24b equal to GCD of 54, 24. 54 can be written like this: 54 equal to 2 into 24 plus 6. So 54 can be written like this. Then take the smaller number 24 and divide that with this remainder, so it can be written like this: 24 equal to 4 into 6 plus remainder 0. So here smallest non-zero value is 6. So GCD will be 6. And second step is to find the integers a and b. Express the remainder as a linear combination of x and y. Our remainder is this 6. So express this 6 as a linear combination of 54 comma 24. 6 equal to 1 into 54 minus 2 into 24. Here a will be 1 and b will be minus 2. It is very simple example. Let's see another example. Let's find GCD of 32 comma 3 and coefficients of this 32 and 3 by using extended Euclidean algorithm. First we need to find the GCD of this 32 comma 3 and then we have to find the coefficients for them. So let us find the GCD of these two numbers. First we need to divide this larger number with smaller number. That can be written like this: 32 equal to 10 into 3, remainder will be 2. Then the smaller number will be divided with this remainder. So 3 equal to 2 into 1 plus 1. This is the smallest non-zero value here. So this will be the GCD. So we will stop here. 1 will be the GCD. And we can go for the next step to find the coefficients for this 32 and 3. First we need to express this GCD as a linear combination of 32 and 3. This equation can be rewritten like this: 1 equal to 3 minus 2 into 1. We can replace this 2 with this equation because we need to express this remainder in terms of 32 and 3. So 3 minus 32 minus 10 into 3, this is coming from here, into 1. If we rewrite this, 3 minus 32 plus 10 into 3, here we have 11 threes and 132. So a equal to minus 1 and b equal to 11. Euler's totient function. Euler's totient function counts the positive integers up to a given integer n that are relatively prime to that number n. Means it will count all the numbers that do not share factor with this number n. For example, if n equal to 9, then 1, 2, 4, 5, 7 and 8, they do not share factor with 9. But if you take 3, 6 and 9, they share factor with 9. So the count of these relatively prime numbers is the Euler's totient function value. So phi of 9 will be count of that relatively prime numbers, that is 6 here. If n is prime, then phi of n will be n minus 1, because except that n, no others will share a factor with number n. So the value will be n minus 1. Suppose if you take 7, except 7, no other will share a factor with 7, means 1 to 6 all are co-prime to this 7. Euler's totient function is associative, means pi of p into q will be defined as pi of p into pi of q, which will be used in RSA algorithm. Then Euler's theorem: a power phi of n is congruent to 1 modulo n. Here phi of n will be the Euler's totient function. This formula will be true if this A and n are co-prime. Means GCD of A and n will be 1. Extended Euclidean algorithm is particularly useful when A and B are co-primes. Two integers A and B are said to be relatively prime or co-prime if the only positive integer that divides both of those numbers is 1. Simply we can say GCD of A comma B will be 1. If GCD of A comma B equal to 1, then there exist two integers x and y such that ax plus by equal to GCD of A comma B equal to 1. With this provision, x is the modular multiplicative inverse of this A over modulo B. A into x plus by equal to 1 mod b. This by becomes 0 because b equal to 0 modulo arithmetic b. Suppose b equal to 3 and y equal to 5, then by will be 15. If we do modulo arithmetic over 3, it will be 0. Means so this term will be 0. A into x will be 1. This A and x are multiplicative inverses of each other over modulo arithmetic b. Similarly, y is the modular multiplicative inverse of b modulo a, because ax equal to 0 mod a, so b into y will be 1 over modulo arithmetic a over modulo a.